Hello, this is Dong-Soo from the Applied Superconductivity Lab. Today we will learn about the coil dimensions and discuss their inner and outer radius, width, and number of turns. This lecture will discuss the coil dimensions of the four geometries of superconducting coils: solenoid, toroidal, racetrack, and saddle. These coil dimensions are similar, but each geometry has different parameters. This slide shows the shapes of the four main magnets in superconducting coils: solenoid, toroidal, racetrack, saddle, and their representative applications. First, the solenoid has a cylindrical magnet coil shape. Its representative applications are MRI for medical devices and NMR for research of molecular structure and properties of substances. Second, the toroidal has a multiple arrangement of D-shaped coils. One application is nuclear fusion. Third, the racetrack is shaped like a running track, and its application is rotating machines such as motors and generators. Finally, the saddle coil has a shape resembling a horse saddle. Its representative application is LHC or Large Hadron Collider, built and operating at the CERN. First, the solenoid. Solenoid is a cylindrical shape with an inner radius, outer radius, half of the coil height, and number of turns. For the dimensionless coil constants, the parameters alpha and beta roughly determine whether the coil is thin and long or wide and short, thus affecting the overall shape of the solenoid. As the parameter values change, the magnetic field also changes, which helps determine the optimized coil dimensions for the magnetic flux density. Second, the toroidal shape. Toroidal is a multiple arrangement of D-shaped coils consisting of small circle curvature, large circle curvature, and straight sections. It can be divided into the inner radius of the small circle, the inner radius of the large circle, the length of the straight section, the coil height, and the number of turns. Here R2, R1, and the length of the straight section L are related by the equation R2 equals R1 plus L divided by 2. The equation R2 equals R1 plus L divided by 2 is one of the design parameters of the toroidal coil. The coil aims to concentrate and maintain a uniform magnetic field to confine plasma within it. Thus, this equation is used to determine the size and shape of the coil based on the equation. Since not all toroidal coils are D-shaped, the equation is only used under specific conditions. Third, the racetrack coil. A racetrack coil can be divided into two parts with two equivalent curvatures and two straight sections. The coil dimensions consist of the inner and outer radius of the circular curvatures, the length of the straight section, the number of turns, and the coil height. Finally, the saddle coil. The constant perimeter winding method at coil ends is a key point for the saddle coil because it describes how the superconducting tape smoothly is wound, while maintaining the constant perimeter and consistently matching with the straight section of the coil without changing its curvatures. To satisfy the condition of the constant perimeter winding, the saddle coil is designed to have a semi-minor axis, A, and a semi-major axis, B, by considering its elliptical shape, natural inclination angle, beta, located on the top of the ellipse, positioning angle, phi, for each new winding, straight section's length, L, and the number of turns. The semi-minor axis is determined by the following equation, while the semi-minor axis value is a design variable. The graph on the below right shows that as the positioning angle and the natural inclination angle increase, the winding strips gradually flatten out with equal curvature. The second significant feature of the saddle coil is the cosine theta winding. The expression for the surface current density that flows through the saddle coil contains a cosine function. So, in the circular cross-section of the saddle coil, the maximum current flows at 0 degrees and 180 degrees, which connects to the cosine theta function on the left figure. For this reason, we use the cosine theta function for the saddle dipole magnet. However, the ideal cosine theta winding is impractical to demonstrate here. Thus, we use a step function that shows that the upper and lower parts of the saddle coil must be empty, and the degree range in the blue boxes in the graph is fixed at 60 degrees. So far, we covered the four main geometrical shapes of superconducting coils: solenoid, toroidal, racetrack, and saddle coils, as well as their representative applications. We have also covered specific design dimensions: dimensionless coil constants for the solenoid, design parameters consisting of radius and length for the toroidal, constant perimeter winding, and cosine theta winding for the saddle coil. Also, one of the significant features of the saddle coil was the constant perimeter winding, which may guarantee a minimum overall strain in the strips of superconducting wire when the strips are bent, preserving the length of every arc.